My current project in telescope making is to make a 10-inch reflector using a Zambuto mirror. Zambuto mirrors have a very high surface accuracy, anywhere between a 20th and a 30th of a wavelength of light, so they're very good indeed. And I've made an 8-inch mirror in the past which has been very successful, but this is a little plan on how to construct the working diagram for a new 10-inch mirror. Now what I've got is I've got a program called 2D Design, which is a simple two-dimensional CAD program, and I've sketched out, I have the existing tube. The tube is in a telescope I've already got, so it's 308 millimeters inside diameter from there to there. This bit here is where the mirror is going to be. If I zoom that over to the middle of the screen, so this is the mirror itself, 10 inches. The program works in whatever units you like, but this is in, I put it into millimeters, so 254 millimeters. It's 20 millimeters thick at the edge, and so this is the curved concave surface here, and that was drawn. Obviously if you take the focal length, double it, and then make a whacking great circle, you get a big circle arc drawn there, and then you construct that and then delete the lines. Then over at the other end, it's 10 inches f5, so the focal length should be 50 inches. So you draw another line here at 50 inches from the mirror, and my current telescope was designed to have a flat field really of only about 14 millimeters, because the CCD chip in the QSI camera was, I think, 18 millimeters. I think I put a little picture of it somewhere up here. Yeah, no, I've deleted that. Oh no, is that it there? Yes, there we go, here it is. So I had, that is the rough size of the CCD. Let me get rid of all these little dotty lines, that's the grid showing. So it's 18 millimeters by 14, and I originally thought, well, all we need to do is to get a circle in the middle being a flat field, but then of course you do get the vignetting at the extreme corners, so you would need 23 millimeter diameter flat field to cover the entire surface of the CCD chip without any loss of light. So if we start with a 14 millimeter size, and then construct at the focal plane a little line which is 14 millimeters from top to bottom there, that's this one here, then you can work out what you can see. Now looking at this, it turned out really it was a little bit for a faster mirror. I've got f6 at the moment, this is going to be f5. It's not going to be so good. Also I'm getting a 30th of a wave secondary mirror. This is the red line is the secondary mirror, inclined obviously at 45 degrees to the light, so the light comes whizzing from your galaxy or star down past here, hits the mirror, reflects all the way back, brought to a focus at this plane here. But of course you then have the 45 degree mirror which reflects it back up and outside. Thank you to Mr. Newton for figuring this out. And this is a little representation of the camera, bits of it at a scale, not the width, just the depths. So away we go. So what you do is you decide where the field is going to be, and then you look at the maximum and minimum sizes you need for the various bits. Now the company I'm getting the precision mirror from do a 2.6 diameter mirror, and then it goes up to 3.1, and I figured that the 2.6 is a little bit on the small side. So this here in dimensions, what I could do is just flip this over. So set up drawing units, let's go inches to sort this out for a little bit. So this wasn't done to the absolute precision, so it's a little bit big, 3.09. I think they do, the thing is actually 3.1. So that's the short axis of the ellipse. The long axis thing is going to be 4.39 inches, and this was the circle that is going to be the support, so that gets glued on. At the moment I've got the circle in the center. Of course, as I'll explain a little bit later, it is a bit down, about 5 millimeters down. So it's either a 2.6 or a 3.1 that I can go for. Obviously you can't be fussy and ask them to make a one-off of another size. So there is the 3.1 or the 4.3 inches. This would be the long axis, 4.3 inches. And if you then go back to your focal plane and look at where the light's going to just pass, so if we go a little bit smaller, if the light that comes in and hits the very edge of the mirror there, and the very edge of the mirror there, it's going to reflect off at various positions, various angles, and it will go sailing along here. And obviously if it hits the mirror, it's going to be of use. So you can imagine that these rays of light, which all go bouncing off the mirror here, are exactly the same as these ones where they would strike the focal plane if the mirror wasn't there. But the geometry of those two groups of rays is exactly the same. So you can then move the 45-degree mirror up and down along this diagonal line here until it just touches this ray of light and just touches that ray of light. So effectively that means that if your eye was looking from this position, anywhere between here and there, you would see the entire surface of the mirror. Look from the side and you're going to be losing light. Now, provided that the CCD element is small enough to fit inside that area, then you're going to have a very good image. So with the larger mirror, that's what we get, and if you puzzle that out, you find miraculously you've now got a 27 millimeter flat field. So the CCD is going to be quite a bit smaller than that, so we should get very little vignetting or darkening towards the corners, the four corners of the picture. That should work out quite nicely. Now, how do we work out where things are going to go? Obviously the main tube is going to be measured from the inside there to the inside there, and then we got to figure out where the focuser is going to be. The focuser will be bolted onto the side of the tube. I've already got one in place on the 8-inch, and obviously that's going to be exactly the same dimensions whether you move it to the 10-inch from the 8-inch. The camera dimensions I have got carefully established by looking at the custom drawing for the QSI WSG. The CCD element is here at the position there, and the front of, they call it a reference surface, so 1.75 inches from the camera's reference to the WSG face. So the front of this part of the camera, the reference surface is 1.75 inches behind that, and if you hunt around in the data you can find that the CCD is a fraction of an inch behind that further still. So little calculations here tell me that from the CCD to the front of the camera will be the 1.75 plus the 0.042, which is that distance there. I have already measured that the front of the camera here to the 8-inch tube is 2.91, so add those two together, we've got 4.705, which is 119.5 millimeters. So when I connect the camera and the focuser onto the side of the tube, it's going to be 4.7 inches or 119. I think I'll go back to the units of millimeters now. Where are we? There we go, millimeters. Okay, so that way you have, the idea is that you want to get the camera as close to the side of the tube as possible. Ideally the camera, of course, would be sitting there at the side. If you plonk the camera, some telescopes do put the camera in the middle here, so that you don't have to worry about a mirror, because obviously a mirror, any inaccuracies in the position or the surface nature of that mirror are going to affect the image. If you had nothing in between and just put if there was if they invented a little camera this big, it would be absolutely wonderful. You could bolt that onto the front of the telescope, and the light would come past it and form a perfect image. But of course the QSI is a massive great thing like this, and if you stuck that in what's called a prime focus, if you stuck that there, it would obscure most of the light, and you wasted having a bigger 10-inch mirror. So clearly, if the camera is way over up here somewhere, too far from the tube, then you're going to not get the image in focus. That's the critical place. So if the camera was further out from here, you would then move the mirror in this direction to the left, and that would throw the rays up, and they would, if you measured from this point here to the focal length and drew an arc around the same, then it would be in that position. The tube of the telescope would be shorter, which is obviously an advantage, but you're going to have to have a massive mirror. If the mirror was then in this position, it would have to be much longer, and you're going to be then cutting out more light. So there is a trade-off. You want the camera to be as far this way as possible, so that you get a smaller mirror, less light obstructed, and if you have the camera in this position over here, it's closer to the tube. It'll follow an arc. It'll do something like following an arc like this, way up here, ideal position, and then down there. Now if it's too close to the tube, the focuser itself, the mechanics which move the camera up and down, are going to be lower and lower and lower. So you want a low profile. On my focuser, I did buy a tube, the focuser tube, which was extra low profile. It's a moonlight focuser, but you're pretty much stuck by the dimensions of the focuser as to how far away you put the camera and the tube, which then tells you where the mirror is going to be. I've also got a coma corrector, which you need for a reasonably fast Newtonian, and that says the coma corrector should be 55 millimeters from the focal plane of the CCD, so it works out quite nicely. You've got 45 millimeters there. You've got this end bracket, not a bracket, as a plate, I suppose, that fits on. Then the coma corrector fits in there, and you arrange the width of that to make it so that the coma corrector is 55 millimeters precisely from the CCD. So that's the setup for that. Now what we look at then down here, the astute viewer will be saying, well, your mirror is way off to one side. This is the tube wall here and here, and if I was to just construct a little rectangle here just for fun, okay, and then I come along and move it, right, so that the rectangle's touching the tube there, it's touching the mirror there. If I drag it over to the other side, we can see that there's now a gap. So the entire mirror assembly is not in the very center of the tube. And if we zoom in on the size, if we zoom in on the mirror itself, here's 111 millimeters, which is the long dimension of the mirror. Chop that into two pieces, so 55.5 and 55.5 to give a center point there. and that 93, by the way, was for a smaller mirror. I think that's a 2.6. So for the time being, I'll just remove that. That's just confusing everybody. So 111, 55, 55. That then is the center of the flat, and this is the optical center of the telescope. So measuring that gives 5.43 millimeters as the offset, which then allows you to calculate how far down you want to shift the secondary mirror to get it perfectly coinciding with the extreme rays that will be going all the way to this point and landing on your CCD. Excuse me. Of course, the CCD is not here, as we explained earlier. It's up on the other side, hiding up there. But away we go. Now there will be then a contraption, the spider. There'll be some cylindrical arrangement here, which is, this is the representation of the cross section of it, which is going to sit in the middle there, with vanes that attach it to the side of the tube, and those vanes of course give stars in a Newtonian reflector characteristic spikes across there. And at the back there will be a mirror cell, which I've ordered from what they call themselves, Aurora Instruments, which is a very fancy one that can hold this mirror absolutely in position. You need to be able to move the mirror up and down in this direction a little bit, and to tilt it to get it absolutely collimated, as the term is, so that it is definitely at 90 degrees, as it were. If we look at this angle here, for the mirror to work at maximum efficiency, the mirror surface should be perpendicular at the center to the middle of the telescope. We call that the optical axis, I think. So the optic axis goes like this, but of course bang, up it goes at 45, off a 45 degree mirror to there. So collimating the telescope when you construct it is quite a tricky thing, because you've got to try and get all of these bits and pieces lined up so that the optical axis is at perfectly 90 degrees with this bend here where it gets reflected. The position of this mirror has to be exactly right, both to and fro, closer to the mirror, further from the mirror, up and down, and the angle, and it mustn't be rotated. So the hardware needs to be fairly rigid. Once you've made it, if you then swing the telescope around in the sky and point to new places, there's not a lot of fun to be had if the mirror here at the back changes in position. You can collimate the telescope perfectly if the telescope's pointing at, say, 45 degrees into the sky. Turn it round, point in the opposite direction, and some telescopes the mirror here will move, or the secondary mirror here will move. So you need a lot of investment in getting the support for this secondary mirror and the support for the primary, and a rigid focuser. Also, you can't have the focuser wobbling to and fro from side to side, and that is where the money comes in. A budget telescope for 150 quid will work perfectly well if you've collimated it and it's got a good mirror. But of course you put it in the back of the car, drive it out to a dark site, set it all up, and it's gone out of collimation. My 8-inch reflector with the Zambuto 8-inch mirror, I collimated it and assembled it in 2015, and I haven't touched it since. It has held its collimation remarkably well. So I'm waiting. All of these bits and pieces have been ordered from the companies. The mirror has been on a 1-year delivery time frame, and I believe is almost ready to be sent. The mirror cell is paid for and on its way, as is the secondary mirror. I haven't ordered the spider yet, but that's because I just wanted to check the support for the spider, and the spider itself seemed to have the wrong or unmatching bolt sizes, so I've sent an email to the company to say what goes on there. So watch this space. with luck it will be complete in a matter of months.